Good day, champ. Welcome back to the channel Analytics Hub. Today's video will be an extension of the numerical analysis playlist, and we will be learning numerical integration. You must agree with me that in calculus, integration finds the exact area under a curve. However, in real-world engineering problems, you often run into two major roadblocks. One, the function f of s is too complex or mathematically impossible to integrate analytically. For example, if you have exponential negative s raised to power 2. And two, you don't have an exact function formula at all. So numerical integration is the branch of numerical analysis used to approximate the definite integral, the integral a to b of f of s ds, using purely algebraic calculations. The primary techniques for numerical integration are divided into two main categories: trapezoidal rule and Simpson's 1/3 rule. Trapezoidal rule approximates the boundary of each subinterval using a straight line turning each section into a trapezoid. This is best fit for a linear polynomial correction. And the Simpson's 1/3 rule approximates the boundary of pairs of subintervals using a parabola, which use higher accuracy for curved data. That is, this is best fit for a second-degree polynomial. If I represent the definite integral of a function of s, the trapezoidal rule is given as open bracket h divided by 2 close bracket multiplied by y subscript 0 plus y subscript n plus 2 open bracket y subscript 1 plus y subscript 2, and you keep adding up until you get to y subscript n minus 1. And h is equal to open bracket b minus a over divided by n. Now let's divide the parameters starting from a. A is the lower limit of integration. It is also called the lower boundary, that is the starting point on the s-axis. B is the upper limit of integration, also known as the upper boundary, and it is the ending point on the s-axis. Now n is the number of subintervals for a particular problem, starting right after the first value. This can also be known as the number of spaces between a data point. An illustration is when you raise up your hand, you have 5 fingers, but in between those 5 fingers you have 4 spaces. That is your number of subintervals. Now h is called step size or interval width. It is the uniform width of each single subinterval, and it is given by the formula open bracket b minus a close bracket divided by n. Now y subscript 0 is called the first ordinate. It is the initial vertical height of the curve at the starting boundary, calculated as y subscript 0 equals to f of a. That is the value of y when you impute the lower boundary to the function. Then y subscript n is the last ordinate. That is the value of y when you impute the value of the upper boundary into the function of s. For our first example, it says evaluate the definite integral from 0 to 1 of s raised to power 3 ds using trapezoidal rule considering 5 subintervals. We have 3 parameters from this question. N is equal to 5, the number of subintervals. A is the lower boundary equals to 0, and B, the upper boundary equals to 1. We can use these 3 parameters to get our step size using the formula b minus a divided by n. That is equal to 1 minus 0, which is 1, divided by 5, which gives us 0.2. Now we use this step size to create our table of value for s and y. So the step size is just like the common difference or the pace that we keep adding from the lower boundary until we get to the upper boundary of s. So since s starts from 0, when we add 0.2 to it, we have 0.2. If we add 0.2 again, we add 0.4. 0.4 plus 0.2 gives 0.6, all the way to 1. Now y is just the function of s given, like the function given here is what? S is power 3, which means when s equals to 0, our y will be equal to what? 0 is power 3, which is equal to 0. When s equals to 0.2, y will be equal to 0.2 raised to power 3, and we can do that here. That is what? 0.2 raised to power of 3. So y is equal to 0.008. Now when s is equal to 0.4, y will be equal to 0.4 raised to power 3. That is 0.064. And that's what I also have here. So you can do that to fill in your y values until you get to the last one, which is when s equals to 1, y will equal to what? Using the trapezoidal rule, the formula is given as h over 2 open bracket y subscript 0 plus y subscript n plus 2 open bracket y subscript 1 plus y subscript 2 plus y subscript 3 or whatever is in between until you get to y subscript n minus 1. Now let's fill in the value. So h is equal to 0.2 divided by 2. Now y subscript 0 is the first ordinate, that is the value of y when you substitute our first boundary, our lower boundary rather, so that is 0. Now y subscript n, that is the last ordinate, which is the value of y when you substitute the higher boundary, which is equal to 1 here. Now plus 2 open bracket y subscript 1, this will be our y subscript 1. What we have to do here is just to fill in all the values of y in between the first ordinate and the last ordinate, because this is it here. This first one here is our y subscript 1, this is our y subscript 2, no, well, sorry, y subscript 0, y subscript 1, this is y subscript 2, y subscript 3, y subscript 4, and the last one is y subscript 5, since n is equal to 5. So y subscript n minus 1 will just our y subscript 4 because n is equal to 5. So when we fill in all the values in between, so we have 0.008, 0.064, 0.216, and 0.512 without repeating this last ordinate. So doing the addition, we have 0.2 divided by 2 is equal to 0.1, open bracket, 0 plus 1 here gives 1, then 2 open brackets. When you add everything here, you should get 0.872, and 2 multiplied by this gives 1.744, plus 1 gives 2.744, multiplied by the outer term, which is 0.1, then our I equals to 0.27 approximately. For example 2, it says evaluate the definite integral from 4 to 5.2 of the natural logarithm of s ds using trapezoidal rule, given that. So here we have been given our table of value for the s and y function. So our s ranges from 4 to 5.2, which is the lower boundary to the upper boundary. Now the y is the natural logarithm of s, which means when s equals to 4, the natural logarithm of 4 is equal to 1.3863 until we get to 5.2. You can confirm that using your calculator. Now we need to calculate our step size h using this formula b minus a divided by n, which is upper boundary 5.2 minus the lower boundary 4 divided by this number of sub-intervals. So how do we calculate the number of sub-intervals? You can do it in two ways. Is either you can count it as the number of spaces in between the data points, or you start counting right after the first value. So for now, let's say I want to calculate the number of spaces between the data points. This is the first space, 1, 2, 3, 4, 5, 6. Or I'll just start counting after the first value. This is the first value, right? So the next one starts from 1, 2, 3, 4, 5, 6. That's how to get the sub intervals. And so 1.2 divided by 6 gives 0.2. That is the step size. And you can also get this by just finding the common difference in s values. So from 4 we move to 4.2 to 4.4, which means 4.4 minus 4.2 gives us 0.2. 4.2 minus 4 gives us 0.2. That is the what step size. Now we impute this into the formula I equals to h over 2. Our h is 0.2 divided by 2, open bracket, our y subscript 0, that is the first ordinate, this is it here, we substitute it back, plus our y subscript n is the last ordinate, 1.6487, plus 2 open brackets, y subscript 1. Now we just fill in the values of y in between, starting from this 1.4351 to 1.6094. So that's what I have here. Now when we add that together, we have the 0.2 divided by 2 gives 0.1. Now for our y subscript 0 plus y subscript n, it gives 3.035 plus 2 multiplied by the addition of these other values of y gives 7.6208. When we multiply that by 2, we have 15.2416. We add that by 3.305, and that gives 18.2766. Now multiply by 0.1. Our final value for the function gives us 1.8277 using the trapezoidal rule. Moving on to Simpson's 1/3 rule. For Simpson's 1/3 rule, we use the general formula A equals to S divided by 3 open bracket F plus L plus 4E plus 2R, and s is equal to open bracket b minus a close bracket divided by n. Now to define the parameters, starting from s is the width of each single sub-interval. It is equivalent to the h in the previous formula, that is step size. Now f plus l is saying the sum of the first and last ordinates, f representing first and l representing last. 4e equals to 4 multiplied by the sum of the even numbered ordinates, so e representing even number ordinate. And 2r is equals to 2 multiplied by the sum of the remaining odd numbered ordinates. Example 1 says a pen moves along a straight guide so that its velocity v in centimeter per second when its distance s in centimeter from the beginning of the guide at time t in seconds is as given in the table below. So we have a value for t and a value for v. So this t is like our s and a v is the function y. The t ranges from 0 to 4.0. So now how do we approach this? We actually draw out the table in a vertical form. So this is the value for t and this is the value for v. We also still need to get our s. Our s is the step size, right? We can also easily get that from by trying to calculate the common difference in the value of t here. So since we have from 1.0 to 1.5, 1.5 to 2.0, which is what is saying there's a common difference of 0.5 here. 2 minus 1.5 is equal to 1.5 minus 1.0, which is equal to what? 0.5. You can decide to label your data points as 1, 2, 3, 4, 5, 6, 7, 8, 9, which means we have 9 values, right? So we'll be focusing on the v values, which are the y function, right? So we have t values, the v values, and the terms in the formula. F plus l is representing the first and the last ordinate, e is representing the even ordinate, and r is representing the remaining odd ordinate. So for this column we'll have just the first ordinate, which is 0, and the last ordinate is also 0, so the sum of these two gives 0. Now for the even ordinate, if 0 here is the first ordinate, which means 4 here is the second ordinate, and 2 is an even number. So I'll be writing that in this column. Now 4 is an even number, so we have 11.68 in this column. 6 is also an even number, so the value for v at number 6 is what? 17.39 is an even number. We'll write it under the even column. Then the last one, 8, is an even number, so 16.08 is the ordinate at an even number 8, that is 16.08. So when we add this together, we have 49.15. Now for the remaining odd ordinate, you just write out the values under the odd number, so 3, 5, 7, 9. So that is, we don't need to write 9 again because 9 is already in the last ordinate. It's representing the last ordinate rather. Now the sum of 7.94 plus 14.97 plus 18.25 gives 41.16. Now substitute all of this into the formula. Okay, I've gotten the value for s here using the formula b minus a over n, that is 4 over 8, that is equal to 0.5. Now the formula says a equals to 0.5 divided by 3, that is s over 3, open bracket, f plus l, the sum of the first and the last ordinate here equals to 0, plus 4 multiplied by the sum of the even ordinate, which are what? 49.15, plus 2 multiplied by the sum of the odd ordinate, which is 41.16. Now when we add that together, 4 times 49.15 gives 196.6, and 2 multiplied by 41.16 gives 82.32. Add them together, you get 278.92 multiplied by 0.5 divided by 3 should give, let's confirm that, 278.92 multiplied by 0.5 divided by 3 should give 46.49, approximately to the second decimal point. For example 2, it says evaluate the definite integral from 0.2 to 1.0 of square root of open bracket 1 plus s power 3 close bracket ds using 8 sub intervals. So solution, we need to calculate our step size s using the formula b minus a divided by n. Now our interval is equal to 8. Now our b is the higher boundary is 1 minus the lower boundary where is what 0.2. So 1 minus 0.2 gives what 0.8 divided by 8, that is what 0.1. Now to fill in the s value, so we just increase from 0.2. We start from the lower boundary and we'll keep increasing it by 0.1 until we get to the higher boundary 1.0. So that is 0.2, 0.3, 0.4 up to 1.0. Now to arrive at the function here is what square root of open bracket 1 plus s is power 3. We can take the mathematical expression step by step. We can first fill in the value for s is power 3. So s is power 3 will be equal to what? When s equals to 0.2, s is power 3 will be equal to what? 0.008. When s equals to 0.3, s is power 3 will be equal to what? 0.027. When we do that up to 1.0, we also have 1.000. Now we can find 1 plus s is power 3. Now 1 plus what we have here gives everything here. Now the square root of 1 plus s is power 3 now gives this. So this will be the function we'll be working with. So we have 1.0039, 1.0134 as our function. So this is the equivalent to our y function, and this is equivalent to, this is our original s function. Now for our f plus l, our e and r. So f plus l is the first and last ordinate, right? So where is the first ordinate? This is it. The first ordinate is equal to this. This is the last ordinate. Now for the even ordinate, this is the second ordinate, so it's actually even. If I skip a gap, then go to the next one, this is another even ordinate, even ordinate, even ordinate. So let me cancel out the first and the last. Then the remaining one are the odd ordinates. Just fill in the other values, then you sum it up. When we sum up everything here, we should have everything on the first and last ordinate. We should have 2.416181 rather. Now substituting into the formula, a equals to s divided by 3 open bracket f plus l plus 4a plus 2r. So a equals to our s equals to 0.1 now divided by 3 open bracket. The sum of the first and the last ordinate gives 2.4181 plus 4 multiplied by the sum of the even ordinate, which is 4.5479, plus 2 multiplied by the sum of the odd ordinate, which is 3.3638. Now we will add this together. We have 0.1 divided by 3 open bracket. The first and last ordinate gives this, plus 4 multiplied by the even ordinate gives 18.1916, plus 2 multiplied by 3.3638 gives 6.7276. Now the sum of these three terms gives 27.3373. Now let's do that. When we have 0.1 multiplied by 27.3373, now divided by 3 again, so we have 0.9112 as our answer. For our last example, it says evaluate the definite integral from 0 to 4 of exponential s ds by Simpson's rule, given that exponential raised to power 1 equals to 2.72, exponential raised to power 2 equals to 7.39, exponential raised to power 3 equals to 20.09, then exponential raised to power 4 equals to 54.60. So we can easily create a table, our vertical table, using the function given. So here we have been given our y function as exponential s, and the values have been given automatically. So we have to fill how many functions we have here. We have 1, 2, 3, 4, and our boundary ranges from 0 to 4. So that is 0 to 4. We are given the value for exponential 1 to exponential 4. Exponential 0 was not given because we know that exponential raised to power 0 equals to what? 1. Hence raised to power 0 equals to 1. So automatically that says that our s is equal to 1, because the common difference between the s value s is equal to 1. It is increasing by 1. Now for our first and last ordinate, our first ordinate is 1, the last ordinate is this, right? 54.60. When we add that together, we have 55.60. Now for the even ordinate, this is our first ordinate, right? So the second one, this second one is an even ordinate, The third one is an odd ordinate. The fourth one is an even ordinate. So when we add that under the column, when we add what we have under this column, we have 22.81. Then for the odd ordinate, we have just 7.39. Substituting this into the formula again, we have s over 3 that is equal to s is equal to 1, then 1 over 3 open bracket. The first and last ordinate gives a total of 55.60 plus 4 multiplied by 22.81, which is the sum of the even ordinates, plus 2 multiplied by 7.39, that is the sum of the odd ordinates. Now when we add that together, when we calculate that, we have 55.60 plus 91.24 plus 14.78, which gives a sum of 161.62. Now divided by 3, our answer for the question gives what? 53.87. And that will be all for today. So you can take these two questions as an exercise. Make sure to subscribe and engage on the channel. See you in the next video. Bye.